All right, guys, let's prove this theorem. Circle theorem 11. It tells us that if two segments are drawn from the same exterior point tangent to a circle, then they are congruent. Okay, how are we going to prove this? Well, let's go ahead and do a two-column proof. Let's make some statements. And we'll need to come up with some reasons. Okay, and what we're being asked to prove, conveniently, we have an if-then statement. So we can pull out our given information. That's going to be our hypothesis. That phrase right after the word if. Okay. And then what we're being asked to prove is going to be the conclusion, that bit right after the word then. They are congruent. So what they want us to prove here in this example, let's prove that AB is congruent to AD. Okay, that is our dashboard. That's our GPS. That's our goal. That's what we're after. Let's jump back to that hypothesis, because that's our given information. That's going to get us started. Two segments are drawn from the same exterior point tangent to the circle. So I'm going to say that AB and AD are tangent to circle C. That's our given. Okay, where are we going to go from there? Well, we could go ahead and draw some auxiliary lines, right? I'm picturing BC and CD, thinking these are going to be relevant, right? Can we draw auxiliary lines, BC and CD? And the reason is 2 points define a line. All right. Okay. If you want, you could formalize it and say BC and CD are radii. You could say that. But you could probably skip that step. One step you don't want to skip, however, though, is just stating that AB, I believe AB, is perpendicular to BC. And AD is perpendicular to CD. How do we know? This is our definition of tangency, right? We're working with the given information which told us that AB and AD are tangent. Based on the fact that they're tangent, we can conclude that these segments must be perpendicular, because that is our definition of tangency. Good. I'm going to go ahead and mark that. All right. Any other ideas here? Probably one other auxiliary line that would be helpful here. Can you see what it is? Let's draw auxiliary line AC. Again, 2 points. 2 points define a line. I'm going to go ahead. All right, I'll just drop a little straight edge on this one because it's a little longer. Okay. All right. Any ideas? I'm thinking congruent triangles. How would I prove that? Are these triangles congruent? How do I know? I'm thinking that BC is congruent to CD. Right? How do I know? All radii are congruent in the same circle, right? Okay. I think that AC is congruent to itself. How do I know that? That's our reflexive property, right? Remember those reflexive pronouns? Things that refer to like myself, herself, itself. It is congruent to itself. That is our reflexive property. Good. Okay. Now, you're probably looking at this and you're saying, hold on, Mr. Rogers, we can't use angle side side, right? That's that one thing that doesn't work for proving triangles congruent. We could use side angle side. We could use angle side angle. We could use angle angle side. We can use side side side. But there's actually one very specific case of this that you can use if and only if you've got a right triangle. Hopefully you remember this one. It's a little more obscure. but it's the one case where if you have a 90-degree angle, it eliminates the ambiguous case, so you know you have congruent triangles. It's called hypotenuse leg, HL. Okay, so I think we can go ahead and declare these triangles congruent. Triangle ABC is congruent to what other triangle? ABC is congruent to ADC. How do we know? We used hypotenuse leg on this. Okay. What can we do from there? Take a look at your dashboard. Take a look at your GPS. Are we approaching our destination? What was our destination? We wanted to prove that AB was congruent to AD. Now that I know these two triangles are congruent, can I go ahead and declare that all of their corresponding parts are congruent? Absolutely. I can say that AB must be congruent to AD, and the reason is corresponding parts of congruent triangles are congruent. There we go. Circle theorem 11 in the books, QED.